Hi, Dave here, and this is video 3. It's the third in a 4-part series of videos on Chapter 13 of Absolute Java on interfaces in inner classes. The focus of this video 3 is to describe interface constants. In video 1, we focused only on the use of method headings. An interface can have method headings, but can also have constants. We'll then look at two interesting interfaces that we will most likely use quite often, provided to us by Oracle, and one's called serializable and the other is clonable. And finally, we'll finish up with talking about best practices for classes that we design. Now, an interface can contain defined constants in addition to or instead of method headings. Any variable defined in an interface must be public, static, and final. Okay, final is the key modifier that says this is a constant. And here I give two examples. For example, public static final string best underscore course equals CSC 230, the course that you are in right now. Notice the naming conventions for constants. I followed our best practices of all caps with words separated by underscores. Now, any class that implements this interface has access to these defined constants. So here's an example of an interface with constants. I've got public interface conversion, and there are 5 different constants defined here. Okay, in this case, they're all double. For example, feet to inches is a double. It's a constant, static, and it's final, and equals 12.0. Now, a class such as demo conversion that implements the conversion interface will have direct access to all of those constants. So down here in the get converted height method of demo conversion, we can directly access the constants that we've inherited from conversion. So here we see us directly accessing the feet to inches constants. Now in Java, unlike C++, a class can have only one base class. And this prevents any inconsistencies arising from different definitions having the same method heading. Okay, so in C++, you could inherit from 2 different classes that have the same method but different bodies. Now, in addition, in Java, a class may implement any number of interfaces. Since interfaces do not have method bodies, the above problem cannot arise. However, there are other types of inconsistencies that can arise. Now, when a class implements 2 interfaces, one type of inconsistency will occur if the interfaces have constants with the same name but with different values. Another type of inconsistency will occur if the interfaces contain methods with the same name but different return types. If a class definition implements 2 inconsistent interfaces, then that is an error, and the class definition is illegal. And Eclipse is real good about catching this and will provide to us the error and describe to us the problem. So here we have the original interface conversion that you saw a few slides back with the 5 different constants. Above it, I show another interface called approximate conversion. Here we kept the same 5 constant names, but 4 of the 5 have different types and been defined as ints instead of doubles. And we create a class called demo approximate conversion. And we implemented both of those interfaces to see what happens when we have a conflict with the same constant defined in both interfaces. And here in demo approximate conversion, I'm implementing approximate conversion and conversion. And once again, down in the get converted height method, I'm referring to feet to inches. And we see the left 2 X error icons provided by Eclipse, and when I hover over feet to inches, it explains to me the error is because the feet to inches is ambiguous. So if we have a conflict between 2 inconsistent interfaces, Eclipse flags it for us. Now, two interfaces that we use quite a bit are serializable and clonable. Let's first talk about serializable. An extreme but commonly used example of an interface is the java.io.serializable interface. And it's interesting, it has no method headings and it has no defined constants. It is completely empty. It is used merely as a type tag that indicates to the system that it may implement file I/O in a particular way. So if we have a class and we say implement serializable, we are signifying to the system that it can take our object and it can save it directly out to an output stream, possibly to a file, possibly over the network. So here's an example. I declared a variable OS of type object output stream, and I set it equal to a new object output stream. Here I create a variable called a student of type student and set it equal to a type of student, to an instance of a student, Alex Dawson. And then I wrote that object out to a string. I can do this because student implements serializable. Now let's talk about just copies, and we'll get to clonable. To make a copy of an object, we could do it in a copy constructor that we learned about in an earlier chapter, or we could do it with clonable. So first I start off with a new student with the first name John, last name Bowden, and I put it into a variable S of type student. In the second case, I create a variable S1 of type student, and I set it equal to the result of using the copy constructor on student, and we passed it the instance S to make a copy of. If we're using clonable, once again I could create an instance of a student. I could then call on that instance the clone method, and I would get back an instance that I put in the variable S1. Now, the big issue is when a copy is made either with the copy constructor or the clone method is whether we are making a shallow copy or a deep copy. So what does this mean? Consider we had a student class that had a first and last name type string, and it had an instance variable called machine of type computer. And computer is a class that we wrote that stored a brand as a string, the memory size in gig as an int, and the model as a string. So let's assume that we created an instance of a computer. The brand was Apple, 8 gigabytes, and it was a 15-inch Mac Pro, and we put that instance into a variable C of type computer. I then called the constructor for student. I passed it a first name of Emily, a last name of Need, and I passed it the address or the reference to the computer. I then called my copy constructor for student, and I passed it S and put the return instance into S1. So I could do this with a copy constructor. Alternatively, I could have set S1 by calling the clone method. In the first case, or this case here, I'm showing that when S was created, let's assume that it was put at memory address 123 for the student. And it has a first name, a last name. But for the computer, it's going to get a memory address of where that instance lives. And let's assume it lives at 2343. When we make a copy of this student object and put it into S1, S1 will get its own memory location. But the issue is, for its instance variables, are they pointing to the same memory location for a computer? If I just copy over their first name, last name, and the value inside a computer, for the computer I'll get the same memory address. So that means both S and S1 have an instance variable that's referencing the same exact instance in memory. So if S changes any of the data members on computer, S1 will see the impact of those changes. This is called a shallow copy. A lot of times we don't like shallow copies because we can have unanticipated side effects or privacy leaks. Now we can, by writing our own copy constructor or paying attention in the clone method, have a deep copy instead of a shallow copy. So here, when we made a copy to a student S1 using a copy constructor or by using the clone method, we're going to pay particular attention that when we get to the computer, that we create a separate computer instance that has the same constants and a different memory address. So here under memory 653, the computer reference will be to a different memory location of 6788 instead of 2343. This is a deep copy, so S and S1 cannot impact each other. Now, the clonable interface, like serializable interface, is an unusual example of a Java interface. It does not contain method headings or defined constants. It's used to indicate how the method clone should be used and redefined. And the goal is to make a deep copy of an object. In other words, an object containing other objects that point to their own memory locations. Now, by default, the method clone of object that we inherit does a bit-by-bit copy of the object's data in storage. So this will give us a shallow copy. And this is okay if the data is all primitive type data or data of immutable class type such as string. We had a first name, last name for Emily Need before, that's fine. This is adequate. Now the following is an example of a simple class that has no instance variables of a mutable class and no specified base class. So the base class is object. So class, your clonable class, we're implementing clonable. We have no data members. So we're saying we're going to override the clone method that returns an object that we inherit. Inside my try block, I'm going to call the object's clone, my parent's clone method, which does a bit-by-bit copy into all the variables. And this has to be inside of a try-catch block. Now, if the data in the object to be cloned includes instance variables whose type is a mutable class, then the simple implementation of clone would cause a privacy leak because it's going to copy the addresses instead of making separate copies. So when implementing the clonable interface for a class like this, either first invoke the clone method of the base class object or whatever the base class is, then reset the values of your own instance variables whose types are mutable class types. And this is done by making copies of the instance variables, by either invoking their clone methods themselves or by invoking their copy constructor. So here's our class employee that we've seen quite a bit. And here employee is going to implement clonable. And notice it's got a date. And this date is going to have a memory location, so it's mutable. And we have an immutable string. We have employee with a copy constructor that we've written. And here we're taking a copy of the immutable string and put that into our own instance variable. But instead of just taking the date, we're going to call the date constructor on the original date to get our own separate memory reference. Okay, so this is a deep copy. Similarly, or in addition to the copy constructor, we could override the clone method. And in our try-catch block, we're going to do a bit-by-bit copy by calling the clone method on our parent, which is going to be an object. We're going to cast that to be of type employee. And then we're going to ask that date instance to call its clone method so we get a separate copy back of the date. So we're doing a deep copy here. Now, alternatively, when I wrote this clone method, If I didn't want to call the objects clone method the bit-by-bit copy, I could just have referred to my copy constructor where I already done all the work of creating a deep copy and return that value. Finally, best practices. When we write our own classes, these are things that you need to consider in every class that you write. Data members should be private. These data members should have their own getters and setters. We probably want a zero-R constructor. We want a copy constructor that will do a deep copy. We want to override the toString method. We want to override the equals method. And we want to implement 3 different interfaces: comparable, serializable, and clonable. That concludes this lecture. Have a great day.